Welcome students to Unit 11, Acid-Base Chemistry. Today we'll be focusing on an introduction to acids and bases, as well as acid-base nomenclature. Acid-base chemistry is known as wet chemistry because acid-base reactions occur in water. This is because water molecules every now and then will collide with one another, transferring a hydrogen ion from one water to another, producing a water with an extra hydrogen ion and a hydroxide ion. This happens very infrequently, as only 1 in every 10 million water molecules actually undergo this process at room temperature. Now, that water molecule with the additional hydrogen ion is known as a hydronium molecule. Hydronium is what we typically characterize as an acid. A solution with additional hydronium ions is typically considered an acid. In fact, it's this extra hydrogen ion that causes acids to be reactive. Those hydrogen ions, which are basically just naked protons without electrons, will tear electrons off of things. This is why when you take metals and place them into acids, which have a large number of hydrogen ions, those hydrogen ions take the extra electrons that metals have to make hydrogen gas. Metals and acids always make hydrogen gas. So water is considered neutral because at room temperature it produces equal amounts of hydronium and hydroxide ions. However, this does set up an equilibrium. So anything that produces more hydrogen ions in solution is considered an acid. For this introduction to acids and bases, we will use the Arrhenius definition of an acid, that an acid is any ionic compound that starts with a hydrogen and is paired with some anion. So the basic simplified formula for an acid we'll use is HA. So if I take a salt containing hydrogen and I place it in water, that adds more hydrogen ions into solution, producing more hydronium. And we'll call this an acid. Bases are compounds that contain the hydroxide ion. Again, this is a simplified version of the definition of a base, but we will use the simplified version that a base is some metal cation as well as the hydroxide anion, because that will shift this equilibrium, producing more hydroxide ions in solution, which is what we will characterize as a base. When it comes to nomenclature, we name compounds based on the bonds that make them up. For example, covalent bonds are made when two nonmetals share electrons. Ionic bonds are formed when compounds transfer electrons from one to another between metals and nonmetals. It's those electrostatic forces that hold ionic compounds together. Acids are unique in the fact that acids are formed from charges and ionized. Therefore, when you place them in water, they do break up into ions, giving us those hydronium ions, giving us those hydrogen ions in water. However, hydrogen is not a true metal. At room temperature, it's not a solid. It doesn't transfer energy particularly well, at least on Earth. So acids are their own category. Because of that, we name acids based on this special category. Now, acids do behave ionically. They do break up in solution, so the naming of an acid is derived from its ionic compound name. So remember, when naming ionic compounds, you name the metal. In the case of acids, it's always going to be hydrogen. And then you name the nonmetal, or the anion. And it's this anion who we will focus on to figure out the name of our acid. So in this first example, example 1 in your packet, we start with H2S, which would be hydrogen, and then sulfur. However, sulfur has a charge. These are ionic compounds, so it's no longer sulfur, it becomes sulfide, symbolizing that sulfur has a negative charge. In example 1, the second problem says H2SO4, that's hydrogen. SO4 is that polyatomic ion you were supposed to have memorized. SO4 with a -2 charge is the polyatomic ion sulfate. Polyatomic ions normally are 8s, meaning sulfate, nitrate, carbonate. However, if you reduce the number of oxygens to make other polyatomic ions, such as the case of SO3 with a -2 charge, you form ites. So sulfate, this would be hydrogen sulfite. Now, it's the ending of these ionic names that we will focus on in order to figure out the name of our acids. So for this first example, we're going to jump around a little bit. Let's start at hydrogen sulfate. If you have an oxyacid that ends in ate, we are going to drop the hydrogen completely from the name and change ate to ic acid. So hydrogen sulfate, H2SO4, becomes sulfuric acid. You can remember it as I ate icky acid. If you have an oxyacid that ends in ite, we drop the hydrogen completely again and change ite to us acid. So hydrogen sulfite becomes sulfurous acid. You can remember this by snake bites are poison us. Ites become us, ates become ick. I ate icky acid, and snake bites are poison us. For binary acids, or when the anion ends in ide, the situation's a little more complicated. We change ide to ic acid. So hydrogen sulfide would be sulfuric acid, but we already have sulfuric acid. So for binary acids, acids in which the anion ends in ide, we just drop the gen from hydrogen, giving us hydro sulfuric acid. Now, I don't have any cute whimsical phrase for you to remember this situation through. If you come up with a better analogy, please come find me and tell me. As I said, binary acids that end in ide get this treatment, where you end up with hydro, the root of the element, and then ic acid. But it is not just binary acids. There are other ones in which the anion ends in ide, such as cyanide. Cyanide is a carbon and nitrogen that have an extra electron. Cyanide would make hydrocyanide if paired with a hydrogen, giving you hydrocyanidic acid. Cyanide is one of the very few polyatomic anions that ends in ide, where this situation would occur. The only two other polyatomic anions that end in ide would be hydroxide, making water, or peroxide, which make hydroperoxic acid, which I am not 100% sure is a thing. In either case, as long as the anion's ending is ide, you will always change it to hydro something ic acid. If it's ate, you will change it to ic acid, and if it's ite, you'll change it to us acid. With that, you're now able to do page 9 in your packet, specifically just the left-hand side. I know that you might not remember your polyatomic anions, so before you pause the video, here are your polyatomic anions that you are expected to memorize. Remember, for my class, anything that is grayed out in these boxes is fair game that you were supposed to have memorized back in Unit 4. Please pause the video and do the left side of page 9 at this time. In order to do the right side of page 9, you have to be able to take the name of an acid and return it to its formula. In which case, it's just a matter of figuring out what the anion is that hydrogen is paired with. So if anything starts with hydro and ends in ic acid, you know that that is most likely a binary acid, meaning it's just hydrogen and some other element. Or you could go the route of looking at what the anion is. Hydrofluoric acid means that it had to have come from fluoride. When it comes to binary acids, you are expected to know what their charges are. Fluoride would be a fluorine atom that has a charge. I grab my periodic table and see that fluorine is one spot away from being a noble gas. So fluorine must pick up one electron, giving it a -1 charge. All acids are paired with hydrogen. So whatever that charge is, hydrogen being +1, will cancel out each negative. Whatever the charge is, that's how many hydrogens you need. So my formula for hydrofluoric acid would simply be HF. For oxyacids, acids that end in "ite" or "us, we will need to know our polyatomic ions. So for carbonic acid must come from carbon 8, meaning I need to know the formula for carbonate. Hopefully you have memorized your polyatomic ions, or Nick the Camel story, to figure out that carbonate is carbon with 3 oxygens that together have a -2 charge. Again, that -2 tells you how many hydrogens you would need to cancel out that negative, giving us a formula for carbonic acid of H2CO3. If an acid ends in "us," it must have come from an "ite." So nitrous acid would come from nitrite. Polyatomic anions that end in "ite" are always one less oxygen than the 8 form. So nitrite would be nitrate, but one less oxygen. Nitrate is NO3 -1, so nitrite must be NO2 with a -1 charge. Again, that 1 tells us we need 1 hydrogen to cancel out that charge, so the formula for nitrous acid would be HNO2. You're now able to finish page 9 doing the right side, so please pause the video and complete page 9. Again, I know that you probably don't remember your polyatomic ions, so pause the video now that the polyatomic ion sheet is in front of you. Lastly, bases are true ionic compounds, and therefore we name all bases like we name any ionic compound. So going from the formula to the name, you simply state what the metal is. If the metal does not have a known oxidation state, specifically it's not in the first 2 columns, it's not silver, zinc, or aluminum, you must provide that oxidation state or charge with a Roman numeral. So for this first example, in example 2, it says NaOH. Na is for sodium. Sodium is in the first column of the periodic table, so we know that it always has a +1 charge, so I don't need a Roman numeral. OH is hydroxide. So NaOH would be sodium hydroxide. CuOH2. Cu comes from the Latin cupric, so this is copper. Now copper is not in the first 2 columns, it's not silver, zinc, or aluminum, meaning it can have multiple oxidation states. So I'm going to need a Roman numeral in order to figure out what the charge is, or in order to state what the charge is of copper. We'll skip that for a moment. OH is pretty straightforward, it's always hydroxide. So in order to figure out the oxidation state of copper, we need to crisscross backwards. So we're going to take this 2, bring it back up. We're going to take this invisible 1, bringing it back up, giving us hydroxide with a -1 charge and copper with a +2 charge. Hydroxide is always -1, so this works out. So this is copper 2. Hydroxide being always -1 means that for the most part, general rule of thumb, you can assume that whatever the subscript is after hydroxide is the charge or oxidation state of any transition metal that forms a base. Lastly, NH3 is on this example because it is unique. There are some compounds that are just naturally bases, and NH3 or ammonia is one such case. You are expected to know that ammonia is a base, and you are not to name it nitrogen trihydride, which would be its covalent name. You are expected to name ammonia, ammonia, because that is a common compound. It would be like naming water dihydrogen monoxide. That would be wrong. We call water, water, just like we call NH3 ammonia. Going from the name to the formula is just a matter of writing an ionic compounds formula. So remember, we just crisscross the charges to neutralize the compound's charge. So for this first one, potassium hydroxide, potassium is on the periodic table. Potassium's Latin name was carbuncle, so it's given the letter K as its symbol. Potassium has a +1 charge because it is in the first column. It is 1 electron away from being a noble gas, so it loses it. Hydroxide's always the same. It's hydrogen and an oxygen that have an extra electron, so OH with a -1. We're going to crisscross those charges down to neutralize the compound. So we're going to take a 1, take the 1, bring it down, giving us K1OH1. So potassium hydroxide's formula is simply KOH. Calcium hydroxide. Calcium is in the second column of the periodic table. It's always a +2. It has 2 more electrons than a noble gas. Hydroxide is OH with a -1 charge. So to neutralize this compound, we will crisscross those numbers down, giving us Ca1OH2. So the chemical formula for calcium hydroxide is CaOH2. Iron 3 hydroxide. Iron is a transition metal, meaning it can have multiple oxidation states. So I tell you what the oxidation state is by providing you this Roman numeral. The Roman numeral tells us that this iron has a +3 charge. Hydroxide remains unchanged. So in order to neutralize the charges, we'll crisscross the numerical values down, giving us Fe1OH3. With that being said, you're now able to do page 8 in your packet. Please complete page 8 and make sure you have completed page 9 for this class. Again, here are your polyatomic ions that you are expected to know and will need in order to complete both pages. Next class, we will start the class by having a nomenclature quiz. Remember, these quizzes are different from my usual quizzes. There is no curve, quote unquote. In order to receive a 100 on this quiz, you must get all 10 questions correct. Much like page 8 in your packet, I'll provide you the name and expect you to give me the formula. Or I'll give you the formula and expect you to provide me the name of acids and bases. Next class, we will be looking at acid-base theory, as well as the beginnings of the pH scale. See you next time.